Should we begin? Okay. Hello, everyone. So here we go again. In lecture 4 out of 4, I decided that maybe it's a good idea to give some references. So whatever happens today, I decided to give them first. Just again, depending on where you're at, some of them might be too basic, some might be not too basic. So if you begin with some sort of overview of general conformal field theory, and here are just two archive references for lecture notes, which I recommend if you haven't seen some things that we discussed before. And then we're discussing Whiteman functions, and that is a very old topic, which pops up here and then there if you read the literature. So this is shamelessly a paper I wrote, which contains a review of these things in reasonably modern language. Then we were talking about Regge theory. And for Regge theory, again, there is a lot of literature, which is more recent. One nice paper is this one. It's called Conformal Regge Theory at Finite Boost. It's one of the more recent papers on this topic. And it has a nice overview and references to older literature if you need that. Then today we're going to talk a little bit about Lorentzian inversion formula and Leitch operators, well, for the duration of one lecture. And so the original reference for Lorentzian inversion formula is this one. And then there's been a lot of follow-ups, but this is the basic one. You can search who cites this and get more results. And for Leitch operators, this is the paper of mine that is mostly the basis for what we're going to talk today. And this is a more recent paper which contains sort of a more maybe kind of, since this paper some things were understood, so it contains a review of kind of more modern state of the field and also some kind of more explicit examples of Leitch operators. So if you want to look that up, that's a good reference. And of course it has other references in it as well. Okay, so that said, let me begin by reminding you quickly where we left last time. So one of the main points of the last lecture was a formula for the 4-point function in the Regge limit. So we were looking at this g of z bar. And just to remind you, to reach the Regge limit in the cross ratio space, we had to take z bar around the cut at 1 counterclockwise. So to signify this fact that we took this sort of monodromy of our correlation function, I'm going to put this counterclockwise arrow in it. And then for this function, we had an expansion which contained a bunch of terms, but the most important term in the Regge limit, up to some prefactors, was an integral over delta. There was d over, and the integral was over d over 2 plus an imaginary number. And then there was a complicated factor here. Most importantly, it depended on, so it was a residue of c delta j divided by 1 minus e to the minus I phi j. Residue at j equals some little j of delta. So this function c delta j just contains information about our theory, like OP coefficients and so on. And here we're looking at the residue of this combination at the rightmost pole in the real part of j. residue of this guy. And then we had kind of some complicated function, but the important factor in it was this dependence, where omega was related to our cross ratios rho and rho bar, where rho was r omega, rho bar was r divided by omega, and Regge limit was omega going to 0. And then there were other terms. Again, this is mostly schematic, it's just the important things. We have some sort of residue of the C delta J, have integral over imaginary values of delta, and we have this factor. So the more complete expression had like other factors in front. It wasn't just omega to the 1 minus delta J, omega to the 1 minus J of delta, and there were other terms as well. So if you want a full expression for what the Regge limit is, that's precisely the subject of this paper. But we are just going to focus on this piece here. And the idea here, okay, first let me introduce some notation that we'll use later. Here, delta is being integrated over these values, d plus I nu, where nu is a real number. So we're just going to parameterize it like so. Now, the point of this J of delta was that in the complex J-plane, we began by from sum over even integers, which we wrote as a contour integral over the poles of so like 0 to 4 and so on. So we wrote the sum that over spins that we had originally. We wrote it as a contour integral over this disconnected contour, picking up the poles of this denominator. And then we deformed this contour into something running along imaginary axis again. In the process of doing so, we might have picked up some additional poles like J, which depends on delta. And in this notation, little J of delta is the rightmost pole. So there might have been others, or some other singularities, but J of delta for us is the rightmost pole. And the reason why we care about the rightmost pole is because the larger the real part of little j, the more singular this is as omega into 0. So the rightmost pole determines how the 4-point function grows in the Regge limit as omega goes to 0. Now, of course, it could have happened that, so for example, if you take this expression, then this expression shows that the 4-point function just grows as a power law in the Regge limit. But of course, this assumes that there exists a rightmost pole. It could have happened that the 4-point function actually didn't grow as a power law, it grew maybe exponentially with 1 over omega. And correspondingly, there might have been poles just extending all the way to the right. So one claim is that this actually doesn't happen. And the reason for this is that the 4-point function can be shown to be bounded in the Regge limit. So we're going to do that, but before doing this, let's get some intuition for what this pole can be. Again, this pole is coming from the singularities of the function C delta J. And we already know some poles of C delta J. For example, we know that when J is an even integer, then our C delta J has poles precisely at the locations of scaling dimensions of has poles in delta at scaling dimensions of various local operators with the given spin. So these are poles in delta. At even integer spin, we are interested in poles in J at imaginary delta. So this is a bit different, of course, from this picture. But you can easily imagine that they're connected. Because where are these poles? These poles in complex delta plane are on the real axis, and they are at scaling dimensions of various operators, various local operators in theory. Of course, we discussed that there are also poles at, let's say this is, there are also poles at places like d minus delta 1, d minus delta 2, and so on, due to the shadow symmetry of this function. So remember, for example, in partial wave expansion was related to conformal block expansion because we could deform the contour for one term to the right and for the other term to the left. So that's where that's coming from. In any case, you have this poles, and this is true for maybe, let's say this is for j equals 4. You have some poles. But now the idea of this Sommerfeld-Watson transform is that we have to work with some sort of analytic continuation of C delta j in spin. So if we imagine that as we analytically continue from, say, 4 to maybe 4.1 in spin, that while all sorts of things could happen, this picture could completely break down and the function could cease being meromorphic. But if we make the simplest assumption that nothing dramatic happens, then at least what should happen is that these poles that we have for our operators, they should move somewhere. You change the parameter spin, and you get they cannot stay constant because as we go, for example, to j equals 6, the picture of poles is completely different. So if they move, if the function remains meromorphic for j between 4 and 6, then the poles should move, and by the time we get to 6, they should settle down in new spots. And of course, the same happens in symmetric fashion to these shadow poles. So in this way, we get the idea that we should have these functions, say delta 1 and generally delta I of j, which describe, if you set, for example, j equals 4 and go over I equals 1, 2, 3, 4, etc., you get all the local operators at spin 4. Now, if you set j equals 6 and make I go 1, 2, 3, 4, and so on, you get all the local operators at spin 6. And for spins between these values, it interpolates somehow. So if you're to make a picture of this, the standard way to draw these functions is in these coordinates. Where you use, as one of the coordinates, you use delta minus d over 2. As the other coordinate, you use j. And so we have some special values of j, the even integers. And we have, on these lines, we know where the poles should be. They should be at some positions of local operators. I'm just making this up. And then there should be symmetric, shadow symmetric pairs, and so on. So this is the picture we start with at even integer spin. And then if we believe in this story about analytic continuation, what we should get is some sort of curves which connect these dots together. And so the way it's believed to look like, and the way you can find it in examples, is something of this sort. Whatever this does, I'm not sure. Something happens. They connect in some way. Which way? That will depend on the theory. Whether this is true is, again, an open problem. In some perturbative examples, you can do these calculations explicitly and see that this is the picture. In non-perturbative theories, it's a little bit of an open question. In any case, starting from this point, starting from this picture, we can try to understand. We can try to begin to understand the possible values for this little j of delta. First, let me notice that here I connected these curves kind of in the symmetric fashion. And this has to do with the fact that we have to have the shadow symmetry. Of course, we can treat our functions delta of j for functions j of delta. And the simplest way to ensure shadow symmetry that between delta and d minus delta is to make sure that j of delta is the same as j of d minus delta for every trajectory. And so these curves should be symmetric, and this is one way for them to connect. It could have also, this particular one could have also done something. Instead of going like this, it could have maybe went here. But there's a theorem which you can prove which says that this particular curve has to be convex. So since it has to be convex, it has to, it basically cannot avoid going this way. I mean, it cannot go this way. If it went this way, it wouldn't be convex. So it has to go like this and join with its shadow somewhere here. And the place where it joins, we usually denote by j naught. Now, the reason why this helps us to understand these functions, let's say this little j of delta, is because here we need to understand poles in j. For delta on this line, it's also called principal series. So when delta is parameterized in this way by nu. So first comment is that when nu is 0, delta is real, it's equal to d over 2. And this point is actually present in our plot. So nu equals 0 is just this line over here. Of course, everything else in this plot is real delta, and therefore imaginary nu, but we want to understand real nu. But at least there is one point of contact. Of course, second comment, which is kind of simpler, is that here we want poles in j. Here I'm talking about poles in delta. But of course, if we have a function which has, say, this sort of term in it, you can view this as a pole in delta. So you fix j and you vary delta and you hit a pole, or you can treat this as a pole in j. So you fix delta, you vary j, and when j solves this equation, being 0, at a pole. So delta and j are described by the same function. In one case by delta of j, in the other case by its inverse j of delta. So what does this picture can tell us about the poles for various values of nu? So when nu is 0, this picture suggests that all the poles are below j naught. Because if you believe in this picture, there are no trajectories coming from above j naught, and maybe there is stuff happening below here, but that all has negative values of j. What happens when we start changing when we start changing nu from 0 to some non-zero values? So let's maybe look at this leading trajectory, this red one, and see how it looks like for small delta minus d over 2. So simply because this has a minimum delta equals d over 2, this trajectory can be described by j naught plus some coefficient times delta minus d over 2 squared plus some higher order terms in delta minus d over 2. Now if you set delta to be d over 2 plus I nu, And of course, what's going to happen, this becomes J naught minus alpha mu squared plus some higher order terms. So we see that while in real delta direction this is a local minimum, in imaginary delta direction, if you imagine being kind of perpendicular to the blackboard, this is actually a local maximum. And this is typical. This is an analytic function. Analytic functions don't have local maxima, local minimum. They have saddle points. So this thing in one direction is local minimum, so in the other direction has to be local maximum. And so what this tells us is that a simple picture is that so if I draw this more carefully, so if now I only draw the poles from C delta J, there is going to be a pole at J naught for nu equals 0. And as we increase nu to positive or negative values, well, at nu equals 0, there could also be other poles below. But as we increase nu, this pole starts moving to the left. And so natural conjecture is that for all value, if you ask for the maximal value of real part of a pole for all possible values of nu, then this is just J naught. That the maximum is achieved at nu equals 0, and then for all other values of nu, things always have smaller real part. Again, this is not something we can prove, perhaps, but it's something that seems to be consistent with all the examples where we can actually do this. And if we believe in this, then we can sort of see what the leading behavior of the 4-point function is. Because now we're looking at integral over nu, and I can rewrite this vector now. So everything else here is omega independent, but if I focus on the omega dependent part, I can write it like this. Write it as I can take omega to 1 minus J naught outside, and then under the integral, I'm going to have e to the power minus absolute value of log omega times alpha times mu squared plus some higher order terms. So what I did is just took this part and replaced little j of delta by this expression. And then for the J naught part, I factored it out, and for the nu dependent part, I wrote it as an exponential. So the main point here is that as you send omega to 0, logarithm of omega becomes large, and this is effectively a saddle point. And you can take this integral by saddle point approximation, but this will produce some weakly omega-dependent term, something like 1 over square root of log omega.
Is it important that the minus sign will receive the positive sign also? It's 1 minus j.
But that's you see, I wrote absolute value of log omega. Log omega is negative because omega is small. So if I don't put absolute value, then it's going to be plus. But then you have to remember that log omega is negative. In any case, the point is that you can take, under these assumptions that I discussed, you can take this integral over nu by saddle point approximation. You can see that the behavior, kind of the leading behavior of the 4-point function in the Regge limit is given by this omega to 1 minus J naught, and the sort of OP coefficients that are relevant to it are those which correspond to the analytic continuation to this point. So because of this point is often called the Regge intercept. Similarly, these trajectories on which we believe that local operators move are called Regge trajectories. Any questions?
And you are talking about examples, like in which examples this has been tested?
So you can make these pictures, say, in N equals 4 with integrability and or other things like fishnet. You can also do perturbative calculations of these trajectories, say in 4 minus epsilon, you see the same sort of pictures. You can always ask, oh, what if there are some operators that we missed and really blah, blah, blah. But in principle, it all seems to be a self-consistent story. We don't have any contradictions to this. I mean, that's a situation typical in a lot of theoretical physics, right? We cannot prove things, but we figure out a picture and we test it in many examples, and then maybe one day somebody will come along and prove this, but generally you just have to learn how things work. Any other questions? All right, so this is the, if you wish, kind of the practical bottom line of Regge theory, that if you study the 4-point function and the Regge limit, which corresponds to this high energy scattering and whatnot, the leading behavior of the correlation function is going to be a power law in this parameter omega, related to the cross ratios rho and rho bar in this way. And if you remember, rho and rho bar were related to the positions where we inserted our operators. And the exponent is related to Regge intercept, which is the point where the leading Regge trajectory intersects the vertical line in this plot. This plot, by the way, is often called True-Fauci plot, this type of plot. And comes from Regge theory in S-matrix context. All right, so I promised you that, so this is our prediction, but I promised you that we know that this 4-point function is bounded. So we're going to prove now that it's bounded. Of course, being bounded implies from this leading behavior that J naught has to be less than 1. So if Regge limit is bounded, follows that J naught has to be less than 1, because of course if it was greater than 1, then this would be a negative power of omega, and this wouldn't be bounded. I should say that this is only true. So if you know anything about n equals 4, you would know that this is not the case in n equals 4 in planar limit. So this is only true non-perturbatively. This is true in any unitary CFT, and it's true non-perturbatively. If you do things like perturbation theory, be it the 1 over n expansion or weak coupling expansion, this might be violated. And the reason for this is that what's bounded is the 4-point function in the absolute ultimate Regge limit, where you make omega, or like make 1 over omega the largest parameter in the theory, or omega the smallest parameter in the theory. If you have something like small coupling or large n, you have to always wonder, oh, is my omega smaller than the coupling, or some power of the coupling, or is my omega 1 over omega larger than n, and so on. And if you do naive calculations in perturbation theory, you might find J naught which doesn't govern this true Regge limit, but rather governs some intermediate regime where, say, omega is small, but not so small compared to the coupling. The coupling is smaller. And then J naught might be different and might not satisfy this condition. So for example, in planar n equals 4, J naught will actually be between 1 and 2, which almost always violates this condition. But this is because initially it will seem that the correlation function is growing as you go into Regge limit, but as you go sufficient far into the Regge limit so that your 1 over omega becomes larger than n, or some power of n, then you'll see that it saturates and stops growing. But this is not an effect that you can see it in the Euclidean order in 1 over n. All right, so why is it bounded? So why is this analytical continued 4-point function bounded. The reason is, let me keep this, just the conformal block expansion in combination with crossing symmetry. So if we step back a little bit, then we began with the conformal block expansion for our 4-point function. So it's a sum over all operators, p coefficient squared, times conformal block, and this came from taking the OP between operators at 1 and 2. So we're looking at phi x1, phi x2, phi x3, phi x4. So we took this OP, but we can also take other OPs. So for example, we can take 1 with 4 and 2 with 3. So this is usually called, the way we were doing is usually called S channel. This way is usually called T channel. S and T differ by switching operators 1 and 3. So in principle, there is just a formula for G of ZZ bar, which corresponds to T channel expansion rather than S channel expansion. To get this formula, it's, in this case, the easiest thing to look at is to just write down the identity which expresses the fact that S channel and T channel are the same, which is that G of ZZ bar is G of 1 minus Z bar times some prefactor Z bar 1 minus Z bar to the power delta phi. So if we now use conformal block expansion, this expansion for G in the right-hand side, with arguments 1 minus Z and 1 minus Z bar, then this is going to be what we call the T-channel expansion. Yeah. Thank you. And, okay, so that's one comment. Another comment is that unlike the S-channel conformal block expansion, T-channel conformal block expansion actually keeps converging in Regge limit. You can go through the analysis and the expansion in T-channel is still convergent. It's not very useful in the sense that it's, as I said before, it's kind of like the Taylor series for the exponent, for the exponential function. It's an infinite sum of terms, and it's really hard to tell which terms dominate and to make any concrete predictions. But nevertheless, we can use it. And so in this proof, we use this expansion. So this is the identity for the usual function, and let's expand it. We get this prefactor to the power delta phi, which is I'm going to denote like so. We have sum over O, phi O squared, G delta O J O 1 minus Z 1 minus Z bar. Okay, so one more fact that we need is that conformal blocks have the property that they have, in this particular case at least, that you can expand them with positive coefficients into powers of their arguments. So this can be written as a sum over some powers h bar, some coefficient a h bar, z to the power h, z to the power z bar to the power h bar. So what's important in this expansion is that this is non-negative, and these coefficients also are non-negative. All right. So this is our formula. Now we can go to Regge limit. To go to Regge limit, remember we had to do this multi-continuation around the branch cut at 1 for the variable z bar. So we need to put this symbol over here. And corresponding on this side, we need every z bar. We need to kind of take around 1 in every term in this sum. Sorry, when I wrote this, this is a mistake. It was in powers of the argument, so it's in powers of 1 minus z, addition 1 minus z bar power h bar. And we need to take this z bar around 1. Of course, in this way, it's easy to see what happens, because when you take z bar around 1, what happens to 1 minus z bar to power h bar is it's just going to get some phase. It's going to get a phase of 2 pi I to the power h bar. 2 pi I times h bar. So 2 pi I h bar will pop out from here. And similarly, this prefactor, which is the same as here, is going to get some phase. So there's going to be e to the I times something coming from the prefactor. But nothing else happens in this expansion. And if all we want is to bound the, say, the absolute value of this function, so we put absolute value everywhere, so then this phase we don't even care about. And when we bound this sum, it's an absolute value of a sum. It's always bounded from above by the sum of absolute values. When we take absolute value of every term, this is non-negative, this is non-negative. This guy is also going to be, in the end, non-negative, because we send z and z bar to 0 along real values. And this phase just goes away when we take the absolute value. So if we replace the equality sign by inequality sign, all we have to do is put absolute values here, and you can get rid of this exponential. And if we assume that the z and z bar are real and small, then we also don't need these absolute values, right? Now, similarly, this is also going to be positive, and I don't need this absolute value either. But after this is just the same as g of 1 minus z, g of 1 minus z 1 minus z bar before we did any LonTI continuations. So the sum, so sum is just g 1 minus z 1 minus z bar times our prefactor, our delta phi, which we know is equal, by the same processing equation that we had here, is equal to, again, this whole sum is equal to just g of z bar. So in the end of the day, what we get is the condition that the absolute value of g of z bar after this LonTI continuation is bounded by g of z bar without doing the LonTI continuation. So again, the logic is we take this guy under the absolute value, we expand it in t-channel blocks, we do the monodromy on every block separately. In fact, we expand each block in the sum of terms, we do monodromy on each term separately. Before the monodromy, all the terms are positive. After the monodromy, all the terms just get some phases. So if you have a sum of positive terms and you add phases in them, you will never make the sum larger, because all the terms were already aligned to begin with. Now we may be making them misaligned, but that will only decrease their absolute value, the absolute value of the sum. And so what this means is that after the LonTI continuation, the result only got smaller than the original value, which was just g of z bar. And now when we are looking on both sides of this equation, if we send z and z bar to 0, which is what happens in Regge limit, then this term is hard to analyze. You need Sommerfeld-Watson resummation and whatever. But this term is just the usual conformal block expansion with z and z bar. And when z and z bar go to 0, it's dominated by the identity operator. And the identity operator just gives contribution equal to 1. So this guy is equal to 1 plus small as z bar go to 0. And so in the limit of z bar going to 0, this shows that the analytically continued correlation function has to be bounded, which is what we claimed it does. So this implies that J naught is less equal to 1, and this in fact provides a justification for the entire conformal Regge theory, because starting from here you can derive, starting from this claim that it's bounded, you can derive the Lorentzian inversion formula, which will provide for you the analytic continuation of the function C delta J in spin, which you can then use in Sommerfeld-Watson resummation to do all these tricks in the first place. But we'll get there. Before we get there, any questions about this? All right, so let's quickly see what the Lorentzian inversion formula does. I'm not going to give a whole lot of details, but basic level, it's before, when we introduced the function C delta J for the first time, we said that this is a function which can be obtained using so-called Euclidean inversion formula, which inverts the conformal partial wave expansion. The 4-point functions have conformal partial wave expansion. If you can think about it as Fourier transform. There is an inverse Fourier transform, which we call the Euclidean inversion formula, and that formula produces for us a definition of this function C delta J. So Lorentzian inversion formula is in a way what Euclidean inversion formula is to conformal partial wave expansion. Lorentzian inversion formula is to conformal Regge theory. So Lorentzian inversion formula in a way inverts conformal Regge theory, but you can just take it on its own and use it as a definition of the function C delta J. So this formula says that function C delta J can be obtained as an integral over z bar. There's some prefactor which I always forget. Z bar to the power d. Then we have conformal block with funny quantum numbers. So what's funny about these quantum numbers is that besides of being shifted, actually the order of J and delta is wrong. So instead of having delta J, instead of delta we have J, instead of J we have delta. And then we multiply it by so-called double discontinuity of the function g z bar. And double discontinuity is defined by taking g of z bar, subtracting 1/2 of the analytically continued counterclockwise z bar, and then also 1/2 of the same sort of function, but instead of taking z bar counterclockwise around 1, we take it clockwise around 1. So this term is just complex conjugate of this one. So the way you prove this formula again, which we are not going to do. The integral here is between 0 and 1 for both z and z bar. And there is also a prefactor, some function. There is a prefactor which is a product of gamma functions. You can find it in one of these references if you want. So the way you derive this sort of formula is by starting with the Euclidean inversion formula, at least one of the derivations, and then writing it in cross-ratio space. So you write the Euclidean inversion formula as also an integral over z bar of just a normal 4-point function with some conformal block, or with some conformal partial waves, which show some of block and its shadow, multiplying it. And then you do clever contour manipulations, and in the end you arrive into this formula. And magically, after all these contour manipulations, it settles down on this funny combination of G with these quantum numbers. The key property of this formula is that boundedness in Regge limit guarantees that it converges. So the Lorentzian inversion formula converges the integral, and it converges for real part of J greater than 1 if delta is if delta is on this principal series of the real part of delta is approximately d over 2. So you don't have to be exactly on the principal series, but if you're in some neighborhood of the principal series, then it guarantees convergence of the Lorentzian inversion formula for all spins with sufficiently large real part, specifically with real part greater or equal to 1. And so, to begin with, when you derive this formula, you derive it for even spins, because the Euclidean inversion formula only makes sense for even spins. So you're just trying to derive a fancier version of the same old C delta J with even integer J. But after you've done all this and you settled on this expression, you realize that this expression makes sense not just for even integer J, but for any complex J with this property. And so, in this way, the Lorentzian inversion formula defines for you an analytic continuation of C delta J in spin. It's a concrete definition. You can analyze, for example, how it behaves at large spin in the right half plane to check that all the things that you need to do with the Sommerfeld-Watson transform are justified, etc. And also, it has this property that it's analytic for sufficiently large real part, which means that we don't have the sequences of poles which go off to the right. And indeed, this precise property is the one which corresponds to boundedness in Regge limit. In general, if the Regge limit is parameterized, the growth in Regge limit is parameterized by J naught, in general, you can actually strengthen this to J greater or equal to J naught. So if J naught is less than 1, then the Lorentzian inversion formula will converge for a wider range of values. So this convergence region is exactly 1-to-1 maps to the result of conformal Regge theory. So for us, for this discussion, Lorentzian inversion formula, we can view it as coming as sort of a posteriori justification of why all this nonsense made sense, why analytic continuation made sense, why Sommerfeld-Watson transform made sense, and why we were justified in assuming analyticity where we needed it. Of course, you can start just from this expression and check that it satisfies all the properties and then do the Regge theory afterwards. So, in the remaining hour, let's discuss light-ray operators. And the point of light-ray operators is to give an interpretation to these Regge trajectories. So in this plot, these orange crosses correspond to local operators. And now we are claiming that there is some nice, interesting curves which are even important for some physics like Regge physics. And the question is, well, can we study them more directly, like this point here, or like this point there? Can we say something more useful about these trajectories rather than just saying, oh, you just compute everything that you know about the theory and then analytically continue that? Because if we don't have such a way, like if we don't have some intrinsic definition for what these trajectories are, it's rather hard to actually understand what they're doing, because if you make a mistake, say you compute some of these scaling dimensions of local operators numerically or something, and you make a little mistake somewhere at spin 100, this is completely going to mess up your analytic continuation. So analytic continuation is like trying to draw an analytic curve through a bunch of points in integer j. That is a very ill-posed problem. It's very hard to do even if you have perfect data. I mean, even if you know exact formulas, actually try to do it numerically, like try to extrapolate a sequence data points, it's very hard. You have to go to very high precision, you have to use very rather involved techniques. So that's the question. Can we find some intrinsic definition for points on these curves? Turns out we can, and this is what Leiter operators are. To introduce Leiter operators, we first go back a little bit to our CFT basics. I mean, not so basics anymore, but we go back to our embedding space stuff. So when we discuss local operators, we, in the real physical space, parameterize them by space-time point x. So x here is an RD minus 1, 1 in Minkowski space, and an null polarization z. So if we work in Euclidean, you have to make z null. In Euclidean signature, you have to make z complex. But in Lorentzian signature, you have the advantage of being able to just put z on the null cone. So you can also take z to be just a real vector. And just to remind you, the definition of this object was in terms of the tensor operator by just contracting the tensor indices with the polarization vector. So we're going to be using this, and part of the reason why using this description is helpful in this context is because it supports the idea of non-integer spin. And the reason for that is if the operator has spin j, the way you can phrase this is that O is homogeneous in Z with degree j. So if you take O of x lambda z, this is the same as lambda to the power j O of x z. And so this, if we restrict to positive lambdas, this property makes sense for any value of j, whereas having pi indices doesn't really make sense. So this is the reason why we're focusing on this. And we're going to need the similar statement in embedding space. So remember, in embedding space, we replace our little x by a vector capital X in the embedding space RD, 2, which is null. And we also consider two vectors as equivalent if they differ by a positive proportionality constant. Now, when we work with operators, we can replace phi of little x by phi depends on capital X. And the property that we need to for this phi is that, first of all, it has to be undefined for capital X, which is null, but also it needs to respect this relation, like this equivalence relation in some appropriate way. And the appropriate way here turns out to be to say that phi is homogeneous in X with degree minus delta, where delta is minus delta phi, where delta phi is the scaling dimension of phi. So this is, in principle, standard way in which you describe primary scalar operators in embedding space. Now, if you want to add spin, then, so if you have operator x and z, you replace it again by an operator which depends on embedding space vector x, and also an embedding space vector z. So z now is also null, but it additionally has to satisfy the property that its inner product with x is 0. Not only that, the operator is to be invariant if you shift z by x. The reason for this is that the polarization vector little z that we had here has d components. If you have this capital Z, has d plus 2 components. So this d plus 2 components, they are null, but so is this little z. It's also null. So that kills one component in both cases. So somehow we need two more conditions to kill the remaining two components, and this is x dot z equals to 0 and z plus alpha x equals O of xz. So these constraints just remove extraneous components from the polarization vector. And again, this is sort of standard embedding space description of primary operators. Maybe it's familiar to some of you. If not, that this is just the rules, how we do it. Any questions about the rules? Great. And similarly to here, if operator has spin j, then here it's homogeneous in little z with degree j. The same thing happens here. If it has spin j, it's going to be homogeneous in the capital Z with the same degree, with degree j. So now that we have this formalism, we can introduce one important concept, which is an integral transform known as light transform. Light transform is a device. It's an integral transform. It takes a primary operator and spits out a primary operator. The way you define it is that you start with a primary operator O. And if you want to explain what is light transform applied to O, well, it's another primary operator. So primary operator is something that you can compute at point x in embedding space and vector z in embedding space. And all I need to do is to define what this is. And the definition is as such. I take integral from minus infinity to plus infinity over a parameter alpha. And what I'm integrating is just O with a funny combination of arguments. So instead of doing O of xz, I do something strange. I do z plus alpha x and put minus x here. Now it turns out that this is a basically up to some unessential choices, this is the only way in which you can write something non-trivial with a single integral, with an integral over one parameter. So let's see why this makes sense. So I'm claiming this is a primary operator. So it has to satisfy a few properties. It has to depend on x and z. Well, it does depend on x and z, so that's easy. Then it has to be homogeneous with respect to x, is degree related to scaling dimension. It has to be homogeneous with respect to z, is degree related to its spin. And it has to be also, it has also to satisfy this condition, that if you shift z by something proportional to x, we get back the same operator. So shifting z is easy to check, because if you shift z by something proportional to x, it just shifts alpha, because here we have z plus alpha x. So if you can compensate any shifts in z by making shifts in alpha. Now let's check homogeneity. So if I replace, say, x by lambda x, then I can pull this lambda out at the expense of writing lambda to the power j in front. So lambda to the power j. And then this one I cannot pull out, but I can replace alpha by alpha divided by lambda. So I replace divided by lambda here and here. So this cancels. And this guy just goes into here, get lambda to the power j minus 1. So it is homogeneous in X, and the degree of homogeneity is j minus 1. Remember that the homogeneity is related to the scaling dimension. And so this operator has scaling dimension, which I'll denote by delta L. It's equal to 1 minus j, where j is the spin of O. Okay, so now let's check Z. So to fix Z, what I'm going to do is I'm going to now multiply alpha by lambda. So I'm going to put lambda here and here. Now that I've done this, I can pull out lambda from the first argument, and I get lambda to the minus delta O. Let me call this JO. And then, of course, have one lambda here. So overall, I get lambda to the power 1 minus delta O. So it is homogeneous in Z. And the degree is 1 minus delta O. This tells me the spin. So the spin of this operator, JL, is 1 minus delta O. So you can see that what happened is that after we applied this light transform to our operator, we got a new primary operator whose quantum numbers have this finite relation to the original quantum numbers. So scaling dimension is related to the original spin, and spin is related to the original scaling dimension. And interestingly, the spin is not necessarily an integer anymore, because scaling dimension doesn't have to be an integer. And so we'll look a bit more in a second at what this transform does. But let me just make one comment here, that you can sort of imagine why this is like getting closer to interpretation of the Lorentzian inversion formula, because Lorentzian inversion formula had this finite conformal block in it, which had scaling dimension spin and exchanged. Now, this operation has exchanged for us scaling dimension and spin. And so, in fact, the difference between this transformation and the thing that you have in the Lorentzian inversion formula is that you just need to apply on top of this the replacement delta goes to d minus delta, and j goes to 2 minus d minus j. So up to this transformation, which is kind of a shadow transformation in scaling dimension, shadow transformation in spin, the slight transform will give you the conformal block in the Lorentzian inversion formula. Now, the reason why it actually shows up there is a bit subtle, but I'm just saying that, you know, it starts looking similar to inversion formula. All right, so what does this transform do? In the sense, okay, we know that it changes quantum numbers, but how does this integral actually look like? Because it's easy to write it in the embedding space, but it's a bit hard to understand what kind of more geometrically in real space what this means. So the first comment is we can analyze what happens to the arguments when alpha goes to the extremes of the integration range. So when alpha goes to minus infinity, we look at the position argument. The position argument looks like minus alpha, which is some large positive number, times minus x. Sorry, here it's supposed to be minus alpha times x plus some 1 over alpha corrections. So this expression here at large alpha looks like this. Now remember that we are working in embedding space, so positions which are related to each other by a positive proportionality constant are the same positions. And ignore the factor minus alpha out front. And so when alpha goes to minus infinity, the position approaches the same position as is defined by x. When alpha goes to plus infinity, we instead have to pull out plus alpha, and then the minus remains here. And so in that case, the position approaches the position described by minus x. So we're doing a one-dimensional integral which starts at x and ends at minus x. Now if you remember our Lorentzian cylinder, x and minus x had an interpretation there. So if you have a point x, then the point minus x corresponded to the point that you obtained by sending null rays to the future and looking for the point where they all collide. So our operator in this expression is being integrated in some way between these 2 points. And in fact, if you work it out, what it's doing, it's being integrated along a null array, just one particular null array. And the direction of this null array is defined by the polarization vector z. Okay. Here, it's the little z attached to this point. So you can do an exercise in which you translate the embedding space language to real space. And under this translation, what you find is that so L of O, the light transform of O, in the usual coordinates to just this physical x, like Minkowski space x, Minkowski space z, is given again by this integral from minus infinity to plus infinity, alpha. Then there is a prefactor minus alpha to the power delta O plus JO. Minus delta O minus JO times O of x minus z divided by alpha, comma z. So this expression is what you get from this expression if you just use the dictionary between embedding space and real space. Now this expression, it's fairly easy to see that it's conformally invariant because we're only doing conformally invariant things. Conformal group acts linearly on these vectors, we're just combining vectors as vectors. Everything is fine, and we check that this operator satisfies everything it needs to satisfy. So conformal invariance in embedding space is obvious. Now the claim is that this expression is also conformally invariant, but it's hard to see when written in this way. Another thing that happens is that the integral over alpha appears to be singular. When alpha becomes positive, we have to choose a branch for this power, etc. There's some singularity when alpha goes to 0. And these are all kind of fake singularities because since our integral goes from x to minus x, these points are in different Poincare patches. We have one Poincare patch which contains x, it's not going to contain minus x. So this problem that appears in this integral, it's actually just a statement that this integral doesn't fit inside one point graph patch, and we are just using bad coordinates. If you used good coordinates like embedding space, then you can see there is no problem. But what this integral does make more apparent is that you can just analyze what happens here. When, first of all, O is being integrated with the same polarization vector all the time, and then the position is when alpha goes to minus infinity, this just goes to 0, and we start at x, at little x, then there is the direction defined by little z, and as alpha goes from minus infinity to 0, this coefficient in front of z gets larger and larger, and so we're just moving along this null line defined by z. This is the picture inside of point graph patch. Inside of Lorentzian cylinder, it looks like this. Any questions? Yeah.
Is there anything sensible applying the light transform twice?
Yeah, if you apply light transform twice, you get back you approximately get back the same operator.
Not the surface?
No, you get back the same operator, except that, in fact, you get a sum of 3 copies of your operator, one inserted at x, one inserted at minus x, and one inserted at kind of the next point. So you get almost the kind of light transform squared is almost identity. It just gives you a sum of operator at 3 different points, which are all conformally linked to each other, so it's conformally invariant. Other questions? All right. So why am I talking about light transform? Turns out that light transform is important for explaining what these guys are. So what light tree operators are. So let me first define light tree operators in some sort of axiomatic way. And then we'll see a bit more explicitly how they show up. So axiomatically, light tree operators the light tree operator is a primary operator, which I'll denote by this kind of boldface L subscript j, like z. So they're primary operators, parameterized in the same way as you would parameterize local operators, so by some space-time point and some polarization vector little z. But they're not local operators, so even though they are parameterized by point, they're not supported at that point, whatever that means. They're not the same as local operators. They're also parameterized by this parameter j, which just determines where on the Regge trajectory you are. So for example, if you want light tree operators associated to this leading Regge trajectory and you set your j to be, I don't know, 5.1, then you are working with this guy. So j just is a coordinate along the trajectory. That's all it does. And in fact, it would be tempting to say that this is the spin of this operator, but it's not, as you'll see in a second. J is not the spin of this operator, it's just a coordinate on this plot. So they transform as primary operators, and their key property is that if we are at even integer spin, and when you look at your Regge trajectory, so we have, Regge trajectory, have this Regge trajectory, there is some sort of coordinate j delta. So if at this value of j, you actually find that there is a local operator sitting on this trajectory, then Oj of xz becomes, so let's say there is a local operator O sitting here, becomes equal to the light transform of this operator x little z. So in other words, for every point on these sort of pictures, we can associate this non-local operator which transforms like a primary and has special property that once your point coincides with a local operator, you can express this non-local guy in terms of that local operator. And the thing that you need to do this is the light transform. So in a way, the operators interpolate between different local operators, but not precisely because in fact they interpolate between light transforms of local operators.
But in which sense it's not local? If you consider like the point function of L-O-Os,
Yeah?
would it be the same power law?
Yeah, it will be a power law, but this is because it transforms like a primary. So the fact that two-point function has some nice form, a three-point function has some nice form, this fact doesn't rely on anything being local, it just relies on transformation laws under conformal transformation. So all that still holds. But it's non-local, as in, for example, the commutators with this operator will not vanish at space-like separations. Like if you have some Weitman function with other things, you have, say, phi at y, then normally the commutator between these guys would vanish. If this was local operator, this commutator would vanish if x and y were space-like separated. Now this is not true anymore. So you cannot use this sort of thing. So this kind of microcausality condition, for example, is violated. Honestly, besides this, I don't know an invariant way of saying that it's non-local. But
like remind this like sort of field between A and I think they depend string.
I'll give an example. So it's not that kind of non-locality. So say disorder string you can make local by doing some tricks, but this you cannot make local by doing tricks. But first let me explain why. So you can like complain, oh, why are you interpolating between these weird light transforms? Why aren't you interpolating between local operators? So there is a good reason for why you cannot interpolate between local operators. And the reason is that if you have a local operator, you can act with it in vacuum and get a state. It's going to be a state in your Hilbert space. If the state is 0, if it happens that this vanishes, if it vanishes for some x and some z, then by doing like translations and boosts, you can show that it vanishes for all x and all z's. And from here, you can actually conclude that the operator is just 0 identically as an operator. So it's the kind of vanishing which we say it vanishes as an operator identity, which means that it might still kind of be non-zero in contact terms and time-ordered correlators, but that just let's ignore this. Basically, it means that the local operator is 0. And the reason for this is that for local operators, if you have some Weitman function where it sits somewhere in the middle, you can always get this Weitman function, as we discussed, by analytic continuation from a Weitman function where this operator sits on the right. Because all the Weitman functions of all the orderings are related to each other by analytic continuations. But if this Weitman function is 0, then all its analytic continuations are 0, and so these Weitman functions are all 0. And so as soon as you insert this local operator in your Weitman function, the local operator vanishes. So basically, annihilating the vacuum is a big no-no for local operators. If you want to have a non-trivial local operator, it absolutely cannot annihilate the vacuum. The only way it can do that is by being 0 itself. But not annihilating the vacuum is a big no-no for these guys. The reason being that if you act with a Elytra operator, And it doesn't matter what precisely do I mean by a Elytra operator. Just some operator with kind of non-integer spin and scaling dimension. If you act with it on vacuum, then because of the quantum numbers, generically the quantum number of this operator, generically the quantum numbers of this operator are going to be like both spin and scaling dimension are going to be non-integer, because generically they are in these pictures. You can show, using representation theory of conformal group, that if this state is non-zero, so if this is non-zero, then you can construct states psi such that the energy is negative in these states. Kind of one way of phrasing this is that the only representations of conformal group which only have positive energies are those corresponding to local operators with integer spins. There are no other positive energy representations of the conformal group. So, and you can also show this in various other ways, but the bottom line is that symmetries dictate that this sort of operators, no matter how you construct them, as long as they have some generic spin and generic scaling dimension, they cannot create states in your Hilbert space. They have to annihilate the vacuum. So it must be that generically, for generic J, this happens. But if it's true for generic J and you want this to be analytic in J, then it's true for all J. And if, in particular, it's true for even integer J. So if you had that this Elytra operator reduced to the local operator itself, this would imply that the local operator annihilates the vacuum, which would mean that the local operator is 0. So this idea that the local operators cannot annihilate the vacuum is in strong contradiction, or like tension, with the idea that if you do manage to analytically continue something in spin, then these things will annihilate the vacuum. And this is why you need this light transform. Light transform, when acting, light transform of a local operator actually does annihilate vacuum. So even though for local operators we have that so if O is not 0, then it doesn't annihilate the vacuum, but the light transform does. And you can check that, for example, by taking 2-point function of O. You can just compute the norm of this Whiteman function. Sorry, compute the norm of this state. And that norm is just the 2-point Whiteman function of O, to which you apply 2 light transforms. And already when you will take the first one, you'll find that this is 0. You can see this by some sort of contour deformation argument. Because to apply a light transform, you integrate over alpha in the definition that I erased. And in the 2-point function, you can just show that you can always deform this contour in a complex plane and get 0. And this has to do with the analyticity properties of the Whiteman function. So that's the key point why you have to have something more tricky than just the local operator itself. Yeah.
You say that these are primaries, but their state is non-integer. Like what SOD2 representations are the highest weight with respect to?
They're not highest weight representations of SOD2. No, I mean that this function transforms as a primary, as in if you take a conformal transformation, you have this guy, then this thing is going to be equal to, some omega of x, some power delta O. Then you're going to have the same guy, x prime, z prime. That's what I mean. I don't mean to say that they're in highest weight representation, because they aren't. Not all representations are highest weight. Does this answer the question? Any other questions? All right. Okay, so that's the statement that you can have these guys. Let's see some example why. Oh, sorry. Before we see an example, one more abstract statement, and that is how they are actually related to what you're doing with the Regge theory. So in Regge theory, one thing that was important was the residue in C delta J of the pole. So when we have poles in C delta J, they come with some residues that we can call R of J. For integer J, so if J is integer, we know that these residues are related to the OP coefficients squared. Now, the claim in terms of Leitcher operators more generally is that there exists this formula for the residue R of J for any spin in terms of the Leitcher operator. And the formula is this. Again, I'm not going to prove it. But you have some prefactor, and then you have the matrix element of the Leitcher operator from the Regge trajectory between the states created by phi's squared. Now, of course, this is a function. This is a function of position of phi, function of position of O, and position of phi. But it's fixed up to an overall constant by conformal symmetry, as was discussed. And so here, really, we divide by some standard 3-point function just to get a number out of this. And similarly, there is a denominator with a 2-point function. Again, the 2-point function is fixed up to an overall constant by conformal symmetry, and so the functional form is fixed. We just divide by this functional form according to our conventions. So this is some standard expression here, and some standard expression here. Now, if you look into the formulas for conformal Regge theory, the place where the residues of C delta J appear, they actually appear not like this. They appear in the combination of like residue of C delta J divided by 1 minus e to the minus I by J. So this is actually no coincidence that we have this factor here, because the natural quantity that ends up entering into Regge theory, as you can see, it's not C delta J, which has to be divided by this weird factor. It's rather this combination purely in terms of Leitcher operators. Okay, so how do we get these guys? And the first construction, kind of the general construction for them, is through a formula which is kind of like an operator lift of the Lorentzian inversion formula. You can lift the Lorentzian inversion formula to operator level, and what it says is that you can get these Leitcher operators as residues at poles in delta of an integral of two scalars, for example, it doesn't matter. So here, this formula will be for Ledger operators which appear with non-zero coefficients in the OP of, say, phi with phi. So integrate phi of x1, phi of x2 with some kernel, which depends on delta and j, x1, x2, xz. And the way you get this kernel is, again, from Euclidean inversion formula. You can write a similar formula which just extracts local operators from an OP of two local operators in Euclidean signature by a similar kernel, which is just a three-point function, conformal three-point function in that case. And what we do to this formula is we apply light transform to it, we do some simple manipulations, and we end up with this definition, which, however, now makes sense for any value of j. And it turns out that if you insert this definition into correlation functions, say you try to, using this formula, try to compute, let's say, this guy here, this matrix element. What you get after small manipulations is precisely the Lorentzian inversion formula. Except that to get there, you need to decide to compute the particular matrix element of this guy. Now, this formula is just at operator level. And this is a construction which is supposed to work in general CFTs, but you can also just take a concrete CFT and ask what it gives you. And in the case of free theory, it's where you can do everything explicitly. So let's look at this leading trajectory in the case of free scalar, where you can write down operators very explicitly. So we're looking at a free scalar. So far it was like up to this formula, no, just before this formula, everything was, if you wish, some sort of axiomatic description of what this operator, what it would mean to have Ledger operators. Now what I'm saying is that there is this general construction which you can in principle apply in any theory, that you can take products of local operators and extract Ledger operators out of them by integrals, and by taking residues. You can use this as a starting point for proving things. For example, you can use this definition to prove this formula, that this is indeed what's happening. Now I'm saying that, okay, let's apply this construction in the concrete theory, in free scalar. Free scalar, it has a fundamental, it has an action, which has a fundamental field phi. And so we can build operators as normal ordered products of phi. So in this case, we can build an operator oj of xz by taking integral d alpha 1, d alpha 2, minus alpha 1 to the power minus delta phi, minus alpha 2 to the power minus delta phi. So far it looks very much like the position space, physical space definition of light transform. And then we take an extra factor of alpha 1 minus alpha 2, absolute value to the power minus j minus 1. And then we have phi of x minus z over alpha 1, phi of x minus z over alpha 2. And this is normal ordered. So if you think about what this means, first of all, it's an expression for an operator. It's an expression for an operator in terms of phis. This is very similar to how you would write local operators. You would write local operators, for example, phi squared, or stress tens are equal to phi times derivative of phi. Now this is a non-local operator, so I'm not taking a product of things at a point, but it's the same sort of definition as you would expect generally in free theory. And the picture here is that we have x, we have our null vector z, we have a null line spanned by z. Now we take on this null line phi's at two different positions described by alpha 1 and alpha 2. So we have phi of x minus z over alpha 1 and phi of x minus z over alpha 2. We integrate over alpha 1 and alpha 2, so these phi's get smeared over this null line, each one of them, but not independently, but correlated with this sort of wave function alpha 1 minus alpha 2. And if you put some correct prefactor here, the purpose of this wave function, well, not the purpose, but first, similarly to what we did for the light transform, you can write this in embedding space. Basically, you remove these two factors, keep everything else the same. Is phi of z minus alpha x, phi of z minus alpha 2x. In the embedding space definition, you can check explicitly that this gives you a primary operator in the same way as we checked for light transforms. And the purpose of this factor is precisely to make it homogeneous with a degree which varies as you vary parameter j. And this formula also allows you to see it explicitly how this is related to light transform. Because what happens when you go to an even integer spin, say j going to, well, let's say 2k, is that with an appropriate prefactor, this in the appropriate prefactor is 1 over gamma minus j over 2. So this prefactor will go to something times delta function for order 2k. So 2kth order derivative of the delta function of alpha 1 minus alpha 2. And then once this happened, you can use it to take one of the integrals, say, over alpha 2, and you're left with one integral, which is just the integral over alpha 1, and you can check that what you're integrating is just a local operator which exists in free scalar, local primary. And indeed, you just get the light transform of that primary. So the reason this happens is, if you want, this is a generalization of the identity that epsilon over x to the 1 minus epsilon goes to delta of x as epsilon goes to 0. This gamma function gives you an epsilon, and this gives you the denominator. Any questions? So this is an explicit example, and what you can do now is you can do more complicated examples. For example, you can consider a product not of 2 phi's, but say of 3 phi's or more. And what happens there is that in two operator case, this wave function alpha 1 minus alpha 2 is fixed uniquely. But if you go to, like, say 3 phi's, then you have to replace it by some sort of wave function, psi of alpha 1, alpha 2, alpha 3, which you have a freedom of choosing. And then if you, say, study this in perturbation theory, you add some interactions, like maybe phi to the 4 interaction, and you go to a fixed point. Then in perturbation expansion, the dilatation operator is going to act non-trivially on the wave function which replaces this. And so you can study the set of Regge trajectories, for example, in perturbation theory. Maybe to put another way, expressions like this, even though simple, and they might be confused by what I wrote here, but even though explicit and just in free theory, they allow you to study these Regge trajectories directly in perturbative theories. So instead of relying on computing a bunch of data for local operators and then analytically continuing, you can just take these expressions and work directly with them, renormalize them as you would renormalize local operators with some, maybe a few extra tricks. And then you can get the shapes of these Regge trajectories point by point. So you can decide, today I'm going to study Regge trajectory at spin pi. And you can get the anomalous dimension at spin pi without doing any analytic continuations. All right, maybe I should stop here. We're just out of time. Any questions about the lecture? If not, let me just say a few words, like what's the point of this? So one point is that, as we hopefully saw in this Regge theory example, you can have various observables which can be important for some, in principle, physical questions like high energy scattering, which are really hard to compute if you only rely on local operator product expansion. But they can be much easier to compute if you allow yourself to use more general tools like Regge trajectories and light ray operators. So that's one approach, that this sort of ideas, they allow you to compute things which would be hard to compute otherwise. And Regge theory is not the only example. There are things like energy-energy correlators, event shapes, and light ray OPs more generally. Another point is that, in principle, in higher dimensional CFTs, we're in this unfortunate situation when we don't have cool things like Virasoro symmetry, which would fix all the structure of the spectrum and allow us to solve the theory. But these Regge trajectories, they kind of offer an interesting possibility that even though the spectrum looks very complicated and chaotic, perhaps, we still expect that it is connected into some structure by this Regge trajectory. So you can go at least between different spins using this idea of Regge trajectories. And so it's not completely, completely unstructured. And moreover, in some examples that we can compute explicitly, well, maybe I should put it differently. There is a conjecture that you can put forward that if you fix all the other quantum numbers like global symmetry charges, etc., that in fact, on this picture that I drew, it's not many different Regge trajectories. It's just one big Regge trajectory with things that we see being just different branches of it which are connected in the complex plane. And we don't really have any evidence against this, but we have a few examples which are, even though being very simple examples, you can check that this is indeed what's happening. And if this is so, then it's an interesting question of can you learn anything from this structure that you have this big analytic curve which somehow incorporates all your local operators. Or even if it's not just one big analytic curve, there is kind of an open question which hasn't been really answered. Is there anything useful you can learn about the structure of the spectrum itself based on this idea of melticity and spin? Okay, so with this very vague motivation for what we were doing, I'll just stop. Thanks for coming.